Hi everyone, welcome to this lecture on the impacts of mining for AP Environmental Science. And we're only looking at one learning objective today, that's topic 5.9. And the enduring understanding is that when humans use natural resources, they alter natural systems, which we'll see as we move forward through this. The learning objectives are twofold. Describe natural resource extraction through mining and describe ecological and economic impacts of natural resource extraction through mining. So basically be able to describe mining itself and then be able to describe the effects of mining. Here's the vocab if you want to pause it and jot this down. And mining is really important. Most of the materials that we get that are not plant or animal in origin come from mining. So a huge wealth of materials. But mining itself is the extraction of valuable geologic materials from the earth that could be in rock or liquid or even gas form. We get a lot of things from mining. So fossil fuels, coal, oil, and gas. So we see both solid, liquid, and gas right there. Uranium, oil for plastics. So most plastics are made from oil. All metals, gems, and rock for building, clay for bricks, groundwater, and you can even mine some fertilizers, most notably phosphates. And then salt is one of the big ones for food. So we get lots and lots and lots of different things from mining, and most of human construction and human goods, if they are not made from plant or animal materials, are coming from the ground in one way or another. And it's really important to note that all resources that we extract from the ground are non-renewable. All of these are non-renewable resources. Now, they are finite. Some are renewable under geologic time. Say groundwater is renewable if you allow that groundwater to recharge. And some of them are so prevalent that it seems as though we'll never run out. A good example of that might be clay for bricks and pottery. I mean, there's different grades of clay and everything, but in general, it'd take a very long time for us to exhaust our resources of clay. The amount of oil on the planet, though, is a lot more finite than clay is. Okay, but we get all of these things from mining and many more. And if we break mining down into two very general categories, we have surface mining and subsurface mining, otherwise known as underground mining. I'm going to start with surface mining as we talk about this. Surface mining is where the overburden is removed to access that deposit, and your deposit is whatever you want to extract, the ore or whatever material it is that you want to extract. Okay? And that material is typically near the surface, so you could just remove the overburden. And the overburden is the rock and soil above that deposit. So I'll show some pictures on the next slides, but we're just literally removing the soil, the vegetation, and the overlying rock above that deposit, whatever it is, setting it to the side or setting it somewhere, and then accessing our deposit from the surface. And we can break surface mining into three large categories, although there are a few others that exist. Strip mining is the removal of overburden and lawn strips to access the deposit beneath. And then the next strip that you use, the overburden fills the previous strip. Okay, so you kind of go in this manner where you dig out one strip, access everything, dig out the next strip. The overburden from that one goes and fills this one. You probably have a bunch of overburden over here from your original strip. And then another one, overburden is used to fill that, etc. Open pit mining is where you just carve a huge pit or a crater into the earth. And mountaintop removal mining is where you remove the top of a mountain to access the material inside of that mountain. Essentially what you do is blast off the ridges and the peaks of that mountain, and that overburden is dumped off the sides of the mountains into nearby valleys. This primarily occurs for coal extraction in the Appalachian Mountains, and it is one of the most ecologically devastating types of mining. All right, so this is an example of a strip mine. This is the Bear Run mine in Indiana. It is a coal mine. And essentially what they are going to do, they're accessing the coal, which is this darker material down here, in these lawn strips. So they dug out one strip and they dumped all their overburden right there on the ground next to it. And then when they go and dig out this next strip, which they probably won't because that looks like private land, like it looks like farmland, but whatever, um, they'll dump that overburden into the previous strip. And they just do it in these lawn strips. And you can see how how their machinery accesses it with these ramps that they leave and everything else. Okay, so that's strip mining. And again, you can see that it's a surface mine because it is at the surface, at the ground surface, and you're not digging tunnels and channels and shafts underground. This is an example of an open pit mine. This is the Twin Creeks gold mine in Nevada. This is a very, very, very large pit. You can see the size of these very large bulldozers or tractors that they use to remove material. This looks like a portal potty for scale, so you probably are very familiar with those for scale. So this is a very large pit. And then an example of mountaintop removal. So let's just say that this mountain in the foreground looked like this mountain in the background. And essentially what they did is they located their coal seam and they started removing the material above that. So they're just blasting off all of this overburden and blasting it down the sides of the mountain one way or the other. And then we have underground mining, also called subsurface mining. This is what you probably think of as miners doing. They're digging tunnels, they're digging shafts into the earth and extracting deposits underground. There's a lot of different types that exist, but we're not really going to get into those. Although I do want to show these pictures. This is from a salt mine in Poland. I'm not even going to try to pronounce what this salt mine is called. This is an underground mine, so they're mining salt out of here. And as I was doing my research, I came across some of these pictures, and it's just like this amazing city carved out of salt and rock underground. It's really, really kind of cool. So it's a tourist attraction now. I don't think that they actively mine the salt out of it, but just thought I'd share these pictures. And like I said, there are other types of mining that are less common. So for example, we could be talking about groundwater mining, which we have and will continue to talk about several times. So this is on the example on the bottom left where you have a house and a well, and that well is extracting groundwater. You could be talking about the in situ leaching of uranium, which they do to recover uranium for both weapons and more commonly for power plants. We could be talking about oil drilling, natural gas extraction, but we'll talk about those on other days when we talk about oil and natural gas in our energy unit. Okay, again, and most of these materials that we mine are finite resources. Now, some of them will be replenished over geologic time, but we're going to treat all resources that we mine as finite because even if they're replenished over geologic timescales, that's not on human timescales. And for something to be sustainably used, it has to be sustainably used over a human timescale, right? It has to be replenished over a human timescale. And we have already gone through many of the readily accessible deposits for pretty much every ore or every material that we want around the planet, because those are the easiest to get. Those are the lowest hanging fruits, right? The stuff that is closer to the surface, the stuff that's maybe in less dense rock, the stuff that is of higher quality or higher concentration. We've already gone through much of that for the different materials that we want to access. We're moving towards, and have been for a while, deposits that are more difficult to access, meaning that there's probably more overburden, there's more cost in accessing those, there's more fuel use for the machinery, all of that stuff. And then also lower quality deposits, which means that there's more impurities, which means that we have to refine those impurities out, which leads to a greater environmental cost and all of the chemicals and water and everything that is used to refine materials. Okay, and there's a ton of different processes, all for different materials that we're not going to get into in this class. So both of those are going to lead to increased costs that are transferred to the consumer, and there's going to become a point with pretty much every material, give or take, where the cost of extracting them is going to be greater than the cost that they can sell it for. So the cost and the amount of resources used will become unprofitable. And we'll go through a couple examples of those, both fossil fuels. So the first one is peak oil. Um, Scientists have been predicting when peak oil will be for several decades, and their predictions have more or less always been wrong. Scientists in the 70s thought that it might be in the 80s or 90s. We know that that isn't the case because we're still using oil. Scientists in the 90s might have thought that it was in the 2010s, but we keep finding new deposits and keep finding new ways to extract oil, such as from tar sands or from fracking, that have extended our use of petroleum. But anyway, peak oil is the theoretical year, which will come eventually because this is a finite resource, at which the rate of petroleum extraction will reach its maximum. After that, it's going to plateau. So in this diagram, it looks like it's maybe, if I could draw a straight line, in the 2020s. Okay, we don't know when it is, but maybe sometime in the near future. Okay, because oil is finite, there's only so much oil. Eventually, the supply is going to run out. But before it does, it's going to prove economically unviable to extract because we're essentially going to, at some point, maybe around like right here, maybe down here, it's going to cost the equivalent of 1 barrel to extract 1 barrel. So once it becomes unprofitable to extract oil, then oil will no longer be extracted, or at least it will for only certain uses. Okay. And needless to say, before we hit peak oil, our oil-based economy really does need to shift in a major way. Another example is coal. Now, coal, we believe that peak coal occurred in 2013 because coal extraction and coal use has declined ever since 2013. So a little bit of history about coal. Coal mines started as subsurface mines just before the Industrial Revolution, when people realized that you can burn this black rock and heat your homes and use it to smelt steel and all of that stuff. And then the Industrial Revolution hit, coal became heavily used, and much of that was from surface mines. Subsurface mines, my bad. With larger machinery, it turned into strip mining, like we saw on the Indiana slide, and then mountaintop removal remining, like we saw in the Appalachian slide. But now that we've cleared out most of the surface deposits of coal, we're moving back again to subsurface mining. So what remains is a little bit more rare, a little bit more less pure in terms of it being anthracitic coal, which we'll talk about when we get to our energy resource unit, and it's moving into the subsurface mining. And this is causing prices to increase, and they have been increasing for the past 50 years or so. Now, obviously, this is a huge generalization, and these 3 stages have occurred at different times throughout the world in different countries as they go through the demographic transition, but in general, this is what we've seen. All right, now let's get into the second learning objective, which is the environmental impacts of mining. So there is a lot of environmental impacts, and we're going to talk about each one of these individually. So the first one that we're going to talk about is the disposal of both overburden and slag. Now, I'm talking about both of these at the same time because the disposal of both of these materials is very similar, but the materials themselves, overburden versus slag, is very different, and where they come from is very different. So overburden has to be disposed of. Recall that overburden is the overlying rock and soil, and often vegetation as well, that is above your deposit. And overburden is greatest in surface mining. Okay. Now you're going to have some overburden, or at least material that you have to remove if you're doing subsurface mining, because you have to dig those shafts and you're going to dispose of that stuff as well. But overburden is definitely going to be greater in surface mining. Okay, that has to be disposed of. If your mine is, right here, then, and all of this outside of that is forest, so you clear cut a patch of forest and put in your mine, you have to have some place to put that overburden. So you're going to move that overburden onto a patch of forest and degrade that patch of forest. That overburden has to be disposed of somewhere. And it's too expensive, too heavy, and there's too much of it to cart it away too far. So typically what they do is dispose of it right next to the mine. Slag is a different product. Slag is a byproduct left from the refining process of raw ore when you're making metals, okay, when you're refining metals. So if you've ever seen somebody smelt iron, maybe in like a history show, or maybe copper, you know that you get a tiny little nugget of iron or a tiny little nugget of copper, and then you get all of this other rock that's waste. That rock that's waste is your slag. Usually it's dumped in the molten phase, so on the top right, we see a train that is carrying slag from a foundry where they're probably smelting, well, they're definitely smelting some sort of metal. And as a molten liquid rock, they're disposing of this slag off of the side of this train track, and they're creating these slag mountains that we see on all these other pictures. Okay, that slag is very heavy and very high in heavy metals. It's typically like solid rock that is just laying there. So it's very difficult for plants to grow on. Imagine this as like, lava rock, right? It's not, but it pours out and flows like lava. It cools like lava, and it's just like solid rock metal right there. And nothing can really grow on that, or at least a lot of things cannot grow on it without going through the stages of secession. Okay. You may see the terms clinker or dross. Those are somewhat similar to slag. They're different, but we don't really have to get into the technical differences, but they have to be disposed of as well, and their disposal is very similar and has the same environmental impacts. Essentially, habitat loss for the most part. And then there's mine tailings. Mine tailings are somewhat similar, but mine tailings are the waste material that's left over after the economic material is extracted. That's at the mine. Okay, so mine tailings are going to occur at the mine. You're going to have some refining at the mine, or some sorting of rock to see what rock has valuable stuff in it, what doesn't, and then a little bit of refining as well, depending on what you're mining. It could be a lot of refining, and you're going to refine it as much as possible just at the mine, so you have less transportation cost to move your ore to the foundry or the factory or wherever it's going next. Okay. And that's all going to create mine tailings. So again, these are the fraction of rock that's left over after the economic material has been removed. Usually it is in an aqueous form. So we have this mixture of water, sand, clay, rock, and all the chemicals that they use to extract the economic material or to partially refine that economic material. Those can be extremely toxic, and these tailing ponds are often very high in heavy metals and other pollutants. Those aqueous solutions are often stored in tailing ponds, which you see up here in the top right. And you notice the different colors of these tailing ponds are due to the different chemicals that are in those. Okay. However, tailings can also be solid. So that's what we see right here. That tailings pile is the solid rock that's left over, and it's just not in an aqueous solution. Okay, so it's just stored as solid rock. Most mines pre-1900 just had tailing piles, and if you go hiking up in the Colorado Rockies and you see like a very old mine shaft, and you can often find the tailing pile right next to the old mine shaft. And a lot of the times those old tailing piles are going to start to be covered by vegetation. But they're still very distinctive as tailing piles because it's rock that's obviously been piled up by humans rather than by a geologic process. Nowadays, it's mostly tailing ponds. Okay. Now, this is where we don't see, this is one of the things that we don't see as consumers. There's a huge amount of waste that's generated from resource extraction. So for example, 1 ton of copper produces 99 tons of tailings. So it's only about 1% efficient. Okay, so imagine that you get your 1 ton of copper that goes to make pipes and makes, electrical wiring and all of that stuff. Only 1% of the rock that was extracted from that mine actually went to make that copper wire. The rest of it is left piled up somewhere, or worse, an aqueous solution somewhere that has to be dammed up and kept and monitored for years to come. Gold is even worse. 5.3 grams of gold produces 1 ton of tailings, so 1 ton of gold produces 200,000 tons of waste rock. And to give perspective, a gold ring is about 3 to 10 grams of gold, depending on the carat. And I don't know gold rings and stuff, but whatever. So let's just say 5.3 grams is average. For that 5.3 gram gold ring that somebody's carrying around, there's a ton of tailings, 1 ton of tailings sitting somewhere. And then that brings us to water pollution. Mining in general uses a lot of water, just vast amounts of water. Just like everything else that we do, it needs water. So much of that water is going to be laden with various types of pollutants. Those pollutants could include arsenic or heavy metals. I have some examples of those heavy metals. A lot of these tailing ponds include different acids, whether that's nitric, phosphoric, or sulfuric acid. For sulfuric acid, always think coal. I have a slide about that in a little bit. And whenever tailing piles are piled there, or any other mining material is piled up, leaching and runoff also occurs and carries pollutants away. That could be as innocuous as just sediments, but it could be heavy metal pollution as well. Okay, all of that wastewater from mining has to be disposed of in some way. Now, there's really no great option for this. One option is to just leave it in tailing ponds. I'll talk about one of the consequences or potential consequences of that on the next slide. The worst case scenario is that you dump it in a nearby river. This occurs in many developing nations around the world, especially where laws and regulations are a little bit lax. Also, worst case scenario, submarine tailing disposal. This is basically where you take your mine tailings and dump them into the ocean or pump them into the ocean via a pipe. That's illegal in the US and Canada, but is practiced a lot in the developing world. Some other options though, subsurface tailings. So you basically pump your mine tailings into porous rock, into porous rock in the ground, like limestone, and you essentially make like a little tailing aquifer. The best case scenario would be if you have, let's say that's the surface of the ground, and you have impenetrable material such as a clay, and then another impenetrable material such as clay beneath that, and between those two layers of clay, you have limestone. You can pump your tailings into that, and they will be confined by those two layers of imporous clay, or impermeable clay, rather. Not a great solution. It can contaminate groundwater, it can contaminate aquifers, and ruin drinking water or irrigation water for people and crops and animals. One of the cool solutions is remediation by bacteria, algae, or plants. This is definitely the most sustainable option, but it only works for certain pollutants. Some of these pollutants can be neutralized or can be metabolized by different organisms, and we can use those different organisms to refine our tailings. All right, so let's look at a local example of water pollution from a mine tailing. Now, I should start this off by saying how tailing ponds are constructed nowadays, and obviously there's going to be lots of variation in their construction or in the way that they're made. Whether based off of when that mine was created, when the mining activity was done, and what type of mining activity it is. But in this case, you can see that there is a tailings pond here. That tailings pond, you can see the remnants of it right now, and you can see that the base of that is plastic or rubber that they put down. So they're going to dig out a pit, line that pit, so that's the ground surface. They're going to line that pit with plastic or rubber, and that ground surface is actually probably going to be on a slope because a lot of mining happens in mountains. So they're going to have to dam it up. Okay, so we have our dam and we have a plastic or rubber lining so that the tailing water does not go and leach down into the soil. So this water is not going to go into the soil. It will instead just stay inside of this tailing pond. That's not foolproof though. This dam can rupture, and if that dam ruptures, that water will go downhill. And that's what happened with the tailing pond at the Gold Keen mine dam that was near Durango, Colorado, or still is near Durango, Colorado. In 2015, the EPA, of all groups of people, accidentally breached the dam while they were doing some cleanup activity. And they released about 3 million gallons of tailings into the Cement Creek, which eventually, or very quickly actually, went into the Animas River. So the Cement Creek is a tributary of the Animas River, which is a tributary of the San Juan, which is a tributary of the Colorado. Okay. Now, it turned the water from bluish green to this rust-colored orange that you see on the top right and on the bottom left with what remains in the tailing pond. Now, the environmental impact was pretty severe, but locally in the Animas River, it wasn't that severe. It was actually a little bit worse into the San Juan and the Colorado. The Animas River, the reason that it wasn't quite as severe is because some stretches of that river are already virtually devoid of life, like before this breach occurred, due to all of the mining activity that's occurred there over the past 150, 170, 180 years. You guys probably know, growing up and living in Colorado, at least many of you, that Colorado is a mining state. Okay, there, through the 1800s, especially, but even still today, a lot of Colorado economy was based around mining. And the EPA was only created in 1970. So before that, people could just dispose of their tailings anywhere and in any way, for the most part, okay, barring any local regulations. And a lot of contamination has already occurred in the Animas River. And it's led to some rivers being, some stretches of the river being devoid of life before this accident. And then some fish populations near Durango sterile, so they're incapable of reproducing. The animus is typically stocked by the Fish and Wildlife Service and is pretty heavily contaminated already. But this is an example of a mine dam failing, or a mine tailing pond dam failing. Okay, and finally, let's just look at coal for a little bit. Coal perhaps is the most heavily polluting natural resource that we consume, specifically mined resource. When you mine coal, you first have to purify that coal-bearing rock to get the coal out of it. You have to wash that coal to remove any surface impurities and anything else. You have to store that coal, and all of that's going to expose it to lots of water. You see the water right here. Maybe this was just right after a rain and your pile of coal. As it rains, on coal, you're typically going to be making a lot of sulfuric acid because coal often has sulfur in it. It often has sulfur content, and the associated rocks often have sulfur content. With the associated rocks, we're often talking about iron 2 disulfide, which is pyrite, also called fool's gold. So in the presence of water, the iron and the sulfur will dissociate. Sulfur will react with the water to create sulfuric acid. Okay, recall that sulfuric acid is H2SO4. Okay, that sulfuric acid can run off into surface waterways. It can leach down into groundwater, and it will obviously lower the pH of any of the waterways that it gets into. Okay. Now, for this part, we're going to talk about coal combustion when we talk about atmospheric pollution. But in general, For right now, just know that coal doesn't just release carbon dioxide in the atmosphere when you burn it, just like burning everything does, but you'll also release some carbon monoxide. You'll release sulfur dioxide from the sulfur. You'll release nitrogen oxides often, and both of those will lead to acid rain, among some other effects, or acid deposition, I should more appropriately say. Okay, so acid rain or acid deposition. But we'll talk about both of those when we get to our atmospheric pollution unit. Coal combustion also releases particulate matter. That includes dust, lead, cadmium, and other heavy metals, as well as arsenic, which isn't technically a heavy metal, it's a transition metal. Anyway, let's get back to the learning objectives. For the essential knowledge, as the more accessible ores are mined to depletion, mining operations are forced to access lower grades. Accessing these requires increased use of resources that can cause increased waste and pollution. So recall that as we have moved through all of the readily accessible deposits, we're moving to those that are less accessible, those that are more difficult to obtain. Just due to that nature of being more difficult to access, it's going to use more resources, oil, petroleum resources most specifically, but it's also going to require more manpower and more time and create more waste in the form of overburden or slag or tailings. Surface mining is the removal of large portions of soil and rock called overburden. Recall that we have three types. We have strip mining, pit mining, and mountaintop removal mining. Okay. And then mining wastes include the soil and rocks that are removed to gain access to ore and waste. So this is the soil and rocks that are moved. That is your overburden. This is not technically correct, called slag and tailings that remain when the minerals have been removed from the ore. So slag is when you are processing that material in the foundry or in the factory, and you're getting the bits of waste rock off of the material that you want, off of the metal that you want, and you're depositing that typically in a molten form. And then tailings are what's being left at the mine itself. So all of the waste rock from the mine itself, not the overburden, but from the mine itself, and then also the aqueous solution of all the chemicals and dissolved rock and all that stuff, dissolved soil and minerals and all that, heavy metals, at the mine itself. Mining helps to provide low-cost energy and material necessary to make products. So we're talking low-cost energy, primarily fossil fuels, also uranium for nuclear energy, and material necessary to make products. So that first slide where we talked about all the materials that we get from mining. The mining of coal can destroy habitats, contaminate groundwater, and release dust particles and methane. We'll talk about the methane release later on in the school year. Especially related to fossil fuels. But realistically, it's not just the mining of coal, it's the mining of really any material that can destroy habitat, contaminate groundwater, and release dust particles. I didn't really focus on it too much because we're going to talk about when we talk about atmospheric pollution, but this dust particle part, whenever you're digging into the soil and it's that soil dries out and it's windy, you got lots of dust. That's particulate matter, and it's a form of air pollution. As coal reserves get smaller due to lack of easily accessed accessible reserves, it becomes necessary to access coal through subsurface mining, which is very expensive. Okay, so coal prices have gone up because of that, and due to that, we hit peak coal in 2013. All right, guys, I hope you have, I hope you learned something. Write down any questions for me to answer in class. I'll see you all later.